Hello and welcome to Engineering Problem and Solution. Today we're going to understand the transient current analysis for RL parallel circuit. So let's find the transient current for the RL parallel circuit. So for that, let's draw the circuit. So let's take the circuit as we have a step current, we have a resistor, and we have inductor in parallel. So we'll say R here, we say L here. So the voltage across resistor we say VR, and the voltage across inductor we say VL. And we can say the current direction plus minus. So we'll say IR, we'll say this current is IL. And we say this is our node voltage, which is VT, or we can also say V, and the step current is applied, and we say IT with a magnitude of I naught. So once we have this circuit, then we can solve the current, which is IR current or IL current, or the transient current of IR or IL. But to do that, we need to know the transient expression of the voltage or VT. So we need to find that first. So I have three simple steps here. If we follow that three simple steps, we can find the transient current of IR and IL, whatever you want to find. So let's apply our step 1. In step 1, what we're going to do is we're going to apply KCL. Now, as I keep saying this, that if you have a circuit, if you have a series circuit, then you apply KVL, which is going to give you expression, and then you can modify that expression to get a differential equation. Similarly, if you have a parallel circuit, then you have to apply, or you can apply, or it's better to apply KCL. And KCL states that KCL is basically Kirchhoff's current law, and it states that sum of the current going in is equal to sum of current going out. So applying KCL at node, and we know we have only one node here. Another node is basically a reference node here. Okay, so this is a reference node, which is also called ground. So applying a KCL at node, we can clearly see that the main current I naught is going to be going in, and other two current, which is IR and IL, is going to out. So I naught is going in, and IR plus IL is going out. So once we have this current going in and out, we can rewrite this current in terms of voltage and resistor. So we know that I naught is a constant, so we keep that as I naught, whereas IR is nothing but VT over node voltage divided by resistor, because that's the current going through this branch here. That's the current going through this branch. And then what about the IL? Now IL has interesting formula, and the formula is 1 over L integration VL, but we don't write VL here because our node voltage is same as the resistance voltage, so we write V here, right? V dt. So I can write as a note. So since, I'll use a different color, since IL is 1 over L integration VL dt. But remember, the point is our VL and the node voltage is same, so we write this as V. So then after, what we can do is to get rid of this integration sign, we can do the derivative on both sides, or we can say differentiate with respect to t on both sides. on both sides. So if we do that, we know this is constant. So derivative of constant is going to be 0. And then we know we have this variable here, and that's a constant divided by constant. So we can say we can keep the constant outside, and then derivative of variable is going to be vt divided by dt, plus the integration is going to go out, or is going to cancel out with because of the derivative. So we're going to get simply vt, or we can say v. Yeah, whatever you like to write. I'm gonna rewrite this as a v, because I'm using v here as vt. So I'm going to write that in the next line. So what I'm going to do now here is 0 equals to 1 over r, and I'm going to write as v divided by vt plus 1 over l times v. Now you can see this is our differential equation, but this is not a standard differential equation. To make a standard differential equation, we need to get rid of this this 1 over r. So if we multiply both sides by r, we're going to get r over l times v equals 0, because that r and r will cancel, and we got dv over dt plus r by l times v equals to 0, because 0 times r is going to be 0. So this is our differential equation. So this is our differential equation. So if you are modeling RL parallel circuit, this is what you should get. This is what the expression, we can say this is equation number 1. This is what we should get in a differential equation term. So I'll write this is first order differential equation for RL parallel circuit. So our step 1 is done. So we are going to move on to step 2 now. So this is for step 1. Then let's move on to step 2. Now step 2 is about solving the differential equation. Now in step 2, we're going to write step 2 here. Step 2 is basically solving the differential equation using a definite method here. We're going to use Laplace transform, but you can use any method you like. You can use power series method, you can use classical method, but we're going to use Laplace transform. So what I'm going to say here, step 2 is solve differential equation using LT. LT stands for Laplace transform. So we need a formula, because the Laplace transform is all about the formulas. So basically, looking at that differential equation, I'm going to use two formula. So let me write that two formula here. So the formula here, which I'm going to use, formula for the Laplace transform. So the first formula, I'm going to use a derivative. So Laplace transform of the derivative, which is dv over dt, is going to give you s vs. Should be capital V, but my small v and my capital V looks same, so don't get confused. So to make things looks different, I'm going to put this s, just to say that it's converted from time domain. This is our time domain v, which we got in the equation. So time domain is converted into frequency domain, means s minus initial condition, which is v0 plus. So once we have that, and then we can move on to the next formula. That's a formula for the derivative. The next formula is basically I need is for variable. So if you have a variable, in our term right now we have v. or we can say Vt. If you apply a Laplace of Vt, you're going to get Vs, capital V. Again, I keep saying that my small v and my capital V are same, so do not get confused on that. Now what we can do is we can apply. Now let's apply, because that is what we are going to do in step 2. Applying Laplace transform in equation 2. Is it equation 2 or 1? Equation 1. So what is our differential equation? So what I'm going to do is I'm going to write that differential equation. We got dv over dt, and we are going to apply Laplace transform plus, and then we have r over L. So Laplace transform of r over L times V. Now r over L is a constant, but remember we need to apply Laplace transform on both sides, but another side, right hand side is 0, so it's not going to be not going to affect anything. Coming back to here, that the derivative Laplace is SVS. So let's write that SVS, and then minus we have V0 plus. So that means we need an initial condition, and I haven't mentioned initial condition on up. We can find the initial condition based on the circuit, so which I'm going to show you in a minute. And then plus we have constant is nothing going to happen with the constant, so constant is as it is, and then we have V t is going to convert with Vs. Vt is converted into Vs. So let me write that Vs equals to 0. Now what we need to do is we need to know what is our initial condition. Now based on the circuit, if you look the circuit here, the circuit is our L circuit, and the initial condition is basically what is happening previously, which is here, or based on the circuit, what is the circuit was in a previous condition. Normally initial conditions should be given to you. If not given, then you can find at t0 minus, and whatever happening in t0 minus, you can transform that to t0 plus depending on the circuit. Now looking at this circuit here, at t0 minus, if we have a switch over there, we can consider the switch is on or off, but we have a step voltage which is always act as on and off, which is like a switch because of step voltage. Now because of on and off, we can think about this is like inductor is charging and is discharging, charging and discharging. Based on that, what really happens with the inductor is that the voltage is going to be behaving very differently than the current. The current or inductor current is going to be same for 0 minus and 0 plus. 0 minus and 0 plus for the inductor, that's the characteristics of the inductor. 0 minus and 0 plus is same, because the nature of inductor is it tries to maintain the same current rate of current same. So yeah, without making too many comments on here, so what I can clearly see that is your V0 plus or initial condition, I can clearly see this is going to be this is going to be open circuit, and whatever voltage is going here is going to be a voltage across this open circuit or V plus. So what I can say here, the initial condition of V0 plus is taken as I naught, because that's the current will go through the resistor, and times R. So that is our initial condition. It should be given. If not given, then you can technically find depending on the circuit, but you need to have some more understanding and more practice before you try to find the initial condition. Anyway, moving on with the initial condition, and the initial condition has been given for V0 plus, which is I naught, and times R, which is basically a constant values. So moving on, so we can see here is SVS, and we can send this I naught R on the other side, and we'll get R over L times Vs equals to I naught times R. And then we can see here that this Vs and this Vs is common. So we can take Vs common, and the leftover is going to be S plus R over L equals to I naught times R. And then we can send this R plus S plus R over L on the other side, and we'll get Vs equals to I naught times R divided by S plus R over L. So this is what we'll get. And this is our second equation. And we are done with our step 2. So we'll write equation 2. And our step 2 is finished. Now we are going to move on to step 3 now. So let's move on to step 3. Now step 3 is basically converting our frequency domain, which is S domain, which is Laplace, to the time domain, which is we have to use inverse Laplace technique. So step 3 is all about applying inverse Laplace. So applying inverse Laplace technique in equation 2. So if we apply inverse Laplace, but remember, to apply that we need to know the formula. So I'm going to write it the formula, and the formula basically here we are going to use is only one formula, and the formula here is inverse Laplace of 1 over S plus A is going to be e power minus at. You can clearly see that inverse Laplace transfer is going to change S domain into the time domain, or frequency domain into time domain. You can see whenever you have a structure like 1 over S plus A, is going to convert into e power at. So if you look the equation 2 now, equation 2 is a similar structure like that 1 over S plus A. So we can say that I naught times R is a constant, so we can move that onto the other side, and we're going to get 1 over S plus R over L, and that is basically structured like this, and we can apply inverse Laplace. So we can say here, so our equation, which is Vs equals to I naught times R, and then I can say this whole thing again multiplying with 1 divided by S plus R over L. And you can clearly see that this thing here, S plus R over L, and the whole thing is looking the similar structure. Now we can applying inverse Laplace transform. I forgot to mention there is another formula I'm using here. So I'm going to say inverse Laplace of Vs, is going to be Vt. So the inverse Laplace of Vs is going to be, let me write this as inverse Laplace of Vs, and then inverse Laplace of, this is constant, literally they can move outside the Laplace, inverse Laplace, but the one thing which is not going to move outside is going to be S plus R over L. So inverse Laplace of Vs is going to be Vt, and the inverse Laplace of is going to be the same, whereas this is going to be e power, because your A this time is this. Remember the formula there, look, A is this, so in this case A is this. That means we're going to get minus R over L T. So that's the formula, or that's the equation. That's the equation of transient voltage for the circuit, for the parallel circuit, for the RL parallel circuit. But what we want here, we want we don't want the voltage, we want the current. So that is what if the voltage is asking. But if the current is asking here, but if we need to find a transient, if we need to find a transient current, but if you look the circuit, which current is we are focusing on? Is it IR or IL? We can find both current basically. If the transient current is what we are interested on, and let's say IR is what we are interested on, then the IR is simply VT divided by R. So whatever we have found, VT, we can put that expression there. So it's going to be I naught times R, times e power minus R over LT divided by R. And then we can see that R and R will cancel. And we are going to get the IR equals to I naught e power minus R over LT. That is our another expression. Similarly, what we are interested is transient current in the inductor. So let's look at that also. Similarly, let's say if we're looking for transient current through inductor then, so here let's say through resistor. What about through inductor? Now remember, I told you the formula for IL is 1 over L, integration VL or V dt. So we can use the same expression here. So we can say IL equals to 1 over L integration, what is our B we got, which is I naught times R times e power minus R over L t and then dt. Now we know that these two are constants, so they can go outside. So we'll get IL, which is I naught times R over L, and then left over is going to be integration E minus R over LT and dt. Then we can simply do the integration here. So let's do the integration, which is IL equals to I naught times R over L, and then integration is basically E minus R over LT. However, it's going to be divide with the same thing, which is minus R over L. So you can see L will go up, R will go down, and we can technically cancel this R and R, this L and L. So what we got then finally? We got IL equals to, but remember, because since it's integration, I forgot to mention about constant C. So I need to mention that constant C there. And then IL is going to be I naught minus e power minus R over L t plus C. Now this C is going to be very important, because this C is going to it should be considered from the initial condition. So if the initial condition is given to us, which is I 0 plus or IL 0 plus or 0 minus, then technically we should be able to get our answer. But looking at that based on the formula, I 0 plus should be 0. So we can consider the C value as 0, but we can leave it as that. Or we can say that is I naught, depending on either it's going to be 0 or it's going to be I naught, whatever value, because it's going to be short circuit or it's going to be open circuit. If it is open circuit, then the I naught C is going to be 0. If it is going to be open circuit, then it's going to be basically 0. but we can leave that as it is, and that is our transient current through the inductor. Yeah, so those are the expression we can find, and that's it.